NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve floor function equations using the definition. We will follow a precise 3-step algorithm and apply it to an example. We will now walk through a complete example, step by step. Solve the equation, floor of 2x minus 1 equals 4. We begin with the definition. If the floor of f of x equals n, then n is less than or equal to f of x, and f of x is less than n plus 1. Step 1. Identify the integer n. Here, the right side is 4, which is an integer, so n equals 4. Step 2. Apply the definition. Replace the floor with a double inequality using n equals 4. That gives 4 less than or equal to 2x minus 1, and 2x minus 1 is less than 5. Step 3. Solve the double inequality for x. First, add 1 to all 3 parts. Then, divide everything by 2 to isolate x. Let us visualize the solution on a number line. A closed point at 2.5 and an open point at 3, with the interval shaded in between. Therefore, the solution set is all x in the interval from 2.5, inclusive, up to 3, exclusive. In this lesson, we will solve the equation floor of 10 to the x equals 0 and build an intuitive picture of why the solution is all negative x values. First, let's write the problem clearly on screen. Step 1. By definition of the floor function, if the floor of u equals n, then n is less than or equal to u and u is less than n plus 1. Here n is 0 and u is 10 to the x. So we get 0 less than or equal to 10 to the x, which is automatically true, and 10 to the x is less than 1. Step 2. Part A says 10 to the x is at least 0. In fact, 10 to the x is strictly positive for all real x, so this part contributes no restriction. X can be any real number. Part B says 10 to the x is less than 1. Because 10 to the x is increasing, we can take log base 10 on both sides. We get x is less than log base 10 of 1, which is 0. So x is less than 0. For intuition, let us graph y equals 10 to the x and the horizontal line y equals 1. The curve lies below 1 exactly when x is negative. So x less than 0 is the set that satisfies 10 to the x less than 1. Step 3. Combine both parts. All real numbers intersected with x less than 0 equals x less than 0. On a number line, that is an open circle at 0, shading to the left. Therefore, the complete solution set is x in the open interval from negative infinity to 0. Example, we will solve the equation, log of the greatest integer of 2x equals 2. Here, square brackets mean the greatest integer, also called the floor function. Step 1. Convert to exponential form. A logarithm with no base written is base 10. So log of something equals 2 means that something equals 10 squared. Applying the definition, we get the greatest integer of 2x equals 10 squared. Step 2. Simplify the constant. 10 squared is 100. So the greatest integer of 2x equals 100. Step 3. Use the definition of the greatest integer function. If the floor of a number equals n, then the number is at least n, but strictly less than n plus 1. Applying that here with n equal to 100 gives 100 less than or equal to 2x, strictly less than 101. Step 4. Solve the inequality for x. Divide all parts by 2 to isolate x. That yields 50 less than or equal to x, strictly less than 101 over 2. In this example, we will solve the equation. The log base 10 of bracket 3x equals negative 2. Step 1. Rewrite the logarithmic equation in exponential form. The definition of a logarithm says, log base b of y equals x if and only if y equals b to the x. Applying that here with base 10 gives, the floor of 3x equals 10 to the negative 2. Step 2. Simplify the expression. A negative exponent means take the reciprocal. That is, a to the minus n equals 1 over a to the n. Therefore, 10 to the negative 2 is 1 over 10 squared, which equals 1 over 100. Step 3. Analyze the floor function. The bracket function here denotes the floor function, also called the greatest integer function. It always returns an integer value. but 1 over 100 is 0.01, which is not an integer, so it cannot equal a floor value. This means there is no real x that satisfies the equation. In this lesson, we will solve a logarithmic equation that includes a floor, also called greatest integer function, following the exact step-by-step structure from the prompt. First, we show the example label. Then we display the problem statement. Log of the floor of 3x plus 40 equals 2. Step 1. Convert to exponential form using the definition of logarithms. The rule says log base b of a equals c if, and only if a equals b to the power c. We show the rule. Applying it here, floor of 3x plus 40 equals 10 to the power 2. Step 2. Simplify the constant power. 10 squared equals 100. So the equation becomes floor of 3x plus 40 equals 100. Step 3. Use the integer shift property of the floor function. For any real a and any integer n, the floor of a plus n equals the floor of a plus n. We show that rule. Since 40 is an integer, floor of 3x plus 40 equals floor of 3x plus 40. Step 4. Isolate the floor term by subtracting 40 from both sides. Then we get floor of 3x equals 60. Step 5. Apply the definition of the floor function. If the floor of x equals n, where n is an integer, then n is less than or equal to x, and x is strictly less than n plus 1. We show that rule. Using n equals 60 and x equals 3x, we get 60 less than or equal to 3x, and 3x is less than 61. Step 6. Solve for x by dividing the inequality by 3. That gives 20 less than or equal to x, and x is less than 61 over 3. Step 7. Express the solution set in interval notation. Because the left endpoint is included and the right endpoint is excluded, we use a square bracket on the left and a parenthesis on the right. So the set of all solutions is the interval from 20 to 61 over 3, left closed and right open. The equation is the greatest integer of log base 10 of open parenthesis 2x minus 1 over 10 close parenthesis equals negative 2. The square bracket means greatest integer. If the greatest integer of a equals n, then n is less than or equal to a, and a is strictly less than n plus 1. So, setting the bracketed expression equal to negative 2 gives us the double inequality. Negative 2 is less than or equal to log base 10 of open parenthesis 2x minus 1 over 10 close parenthesis, and that is strictly less than negative 1. We'll write it as a system to solve each side separately. Let's solve the left inequality. Because our base 10 logarithm is increasing, log of a greater than or equal to b means a greater than or equal to 10 to the b. So we get 2x minus 1 over 10 greater than or equal to 10 to the power negative 2, which is 1 over 100. Adding 1 over 10 to both sides gives 2x greater than or equal to 1 over 100 plus 1 over 10. Divide both sides by 2 to isolate x. Now, the right inequality. Again, because log base 10 is increasing, log of a strictly less than b means a is strictly less than 10 to the b. So 2x minus 1 over 10 is strictly less than 10 to the power negative 1, which is 1 over 10. Add 1 over 10 to both sides to get 2x strictly less than 2 over 10. Finally, divide both sides by 2 to get x strictly less than 1 over 10. A quick domain check for the logarithm. The inside must be positive. 2x minus 1 over 10 must be greater than 0. That gives x greater than 1 over 20. Therefore, the solution set is the intersection of the two inequalities, from 11 over 200 inclusive to 1 over 10 exclusive. Let's display the problem clearly on screen. Step 1. Simplify the exponents. We know that 1 over 9 equals 3 to the power of negative 2. Since both sides now share the same base 3, and the base is positive and not equal to 1, we can equate the exponents. That gives the floor of log base 1/2 of x equals negative 2. Step 2. Use the floor function. If the floor of a number equals negative 2, then the original number lies in the interval from negative 2 inclusive to negative 1 exclusive. So we write negative 2 is less than or equal to log base 1/2 of x, which is less than negative 1. Let's visualize this interval on a number line. Step 3. Solve for x from the logarithmic inequalities. Because the base 1/2 is between 0 and 1, the logarithm function with this base is decreasing, so inequalities flip when we exponentiate. From -2 less than or equal to log base 1/2 of x, we get x less than or equal to 1/2 to the power -2. From log base 1/2 of x less than -1, we get x greater than 1/2 to the power -1. Put together, we have 1/2 to the -1 less than x less than or equal to 1/2 to the -2. Step 4. Compute the bounds. 1/2 to the -1 equals 2, and 1/2 to the -2 equals 4. Therefore, 2 is less than x, and x is less than or equal to 4. That is, x belongs to the interval open to, closed 4. Let's display that solution on an x number line as well. Quick check. Try x equals 3, which is between 2 and 4. Log base 1/2 of 3 is between -2 and -1, so its floor is -2, and 3 to the -2 equals 1/9. It works. Final answer. The solution set is the interval open to, closed 4. Example. We will solve the equation, floor of sine x plus cosine x equals 0. Our plan is to translate the floor condition, rewrite the trig sum, and read the allowed angles from an intuitive unit circle and number line. Step 1. Use the floor function definition. If floor of u equals 0, then u must be at least 0 and strictly less than 1. Applying this to our expression gives 0 is less than or equal to sine x plus cosine x, and that is strictly less than 1. Step 2. Rewrite the sum using a standard identity. Sine x plus cosine x equals square root of 2 times sine of x plus pi over 4. Substituting this into our inequality gives 0 is less than or equal to square root of 2 times sine of x plus pi over 4, which is strictly less than 1. Divide everything by square root of 2, and we get 0 is less than or equal to sine of x plus pi over 4, which is strictly less than 1 over root 2. From 0 to less than pi over 4 translates to x from negative pi over 4 up to 0, not including 0. The second arc from greater than 3 pi over 4 to pi translates to x from greater than pi over 2 up to and including 3 pi over 4. Let us place these on a number line from 0 to 2 pi. Let us check the boundaries to confirm inclusion and exclusion. At x equals 3 pi over 4, sine plus cosine equals 0, so floor is 0, included. At x equals 7 pi over 4, sine plus cosine equals 0, included. At x equals pi over 2, sine plus cosine equals 1, not included. At x equals 0, sine plus cosine equals 1, not included. Finally, include periodicity by adding 2k pi for any integer k. The full solution set is x in the union of open from 2k pi plus pi over 2 to closed at 2k pi. Periodicity by adding 2k pi for any integer k. The full solution set is x in the union of open from 2k pi plus pi over 2 to closed at 2k pi plus 3 pi over 4, and closed at 2k pi plus 7 pi over 4 to open at 2k pi plus 2 pi for all integers k. The problem is floor of sine x plus floor of cosine x equals -1. To analyze floor expressions, remember the key rule for the floor function. If the floor of u equals n, then n is less than or equal to u, and u is strictly less than n plus 1. Step 1, case 1. We let floor of sine x be -1, and floor of cosine x be 0. This means sine x lies between -1 inclusive and 0 exclusive, and cosine x lies between 0 inclusive and 1 exclusive. From the quadrant picture, sine negative and cosine non-negative means we must be in the fourth quadrant. The angles range from 3 pi over 2 inclusive up to 2 pi exclusive for each 2 pi cycle. Let's record that interval. Quick challenge. Can you predict the other case that sums to -1? Think for a moment. Okay, let's proceed. Step 2, case 2. Now we set floor of sine x equal to 0 and floor of cosine x equal to -1. That means sine x lies between 0 inclusive and 1 exclusive, and cosine x lies between -1 inclusive and 0 exclusive. From the quadrant picture, that puts us in the second quadrant. Angles range from just after pi over 2 up to pi inclusive in each 2 pi cycle. Let's write that interval now. Step 3, combine the two cases. The general solution is the union of those intervals across all integers k. This is our final answer. In this lesson, We will solve a floor function equation step by step and visualize the final answer on a number line. First, let's show the problem as an example. The equation is the greatest integer of open parenthesis 2x plus 1 over x close parenthesis equals 7. Step 1. Simplify the fraction by splitting it over x. We use the fraction splitting rule. A plus b over c equals a over c plus b over c. Applying that, we rewrite the inside as 2x over x plus 1 over x. Step 2. Reduce 2x over x to 2. That gives us, open bracket, 2 plus 1 over x, close bracket equals 7. Step 3. Use the property of the floor function that allows taking an integer out of the brackets. The rule is floor of x plus n equals floor of x plus n for any integer n. Applying this, 2 plus floor of 1 over x equals 7. Step 4. Isolate the floor expression by subtracting 2 from both sides. We get floor of 1 over x equals 5. Step 5. Apply the definition of the floor function. If the floor of u equals n, then n is less than or equal to u, and u is strictly less than n plus 1. So 5 is less than or equal to 1 over x, and 1 over x is less than 6. Step 6. Solve for x. Since 1 over x is between 5 and 6, it is positive, so x must be positive. Taking reciprocals flips the inequality directions. 1/6 is less than x, and x is less than or equal to 1/5. Therefore, the solution set is the interval from 1/6 not included up to 1/5. Included, we write d equals open parenthesis 1/6 comma 1/5 close bracket. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.